These are the problems at the back of the book. So I'll just focus on somewhat those that are harder probably. And also I'll be monitoring the time. So problem 11.38 states here that calculate the number of spheres that would be found within a simple cubic, a body-centered cubic and a face-centered cubic. So I already discussed this the last video. Again, for simple cubic, there are 8 at the corners. Uh, each of those 8 is measured as 1/8 because only 1/8 of those spheres will be included in a particular cell. So 1/8 times 8, that would be 1. So for a simple cubic, there is only one atom. Okay? You go back to the drawing. For a body-centered cubic, there are those 8 at the corners and there is one at the body. So there are two. One for the body and then one for all the 8s at the corners, which is measured as 1/8. Okay, so there are two. And for a face-centered cubic, there are four. So again, at the face, the all the atoms is counted as one half. So there are six faces. So there are basically three. So six times one half, that would be three atoms at the face. So three atoms at the face, and you have again eight at the corners. You have three plus one. That should be equal to four total number of atoms in a face-centered cubic cell. 11.40 Barium metal crystallizes in a body-centered cubic lattice. The barium atoms are at the lattice points. The unit cell edge length is 502 picometer. Again, go back to our using the prefixes. That is read as picometer. Pico is times 10 to the negative 12. So micro is negative 6. Milli is negative 3. Micro is negative 6. You go back to the table. Micro is negative 6. Nano is negative 9. Nano, pico, fico, pico, feto, ato. So, pico is in the range of negative 12. And the density, so we will start solving this one. Barium, barium is a BCC, so we have to take note of that. So, we are faced with barium. So, barium, BCC. So, you just so this is a BCC, a body-centered cubic. So what are the properties? What are the given? So we will term this as whereabouts. So whereabouts, given, and what is asked. So we were given barium, which is a BCC, and then the unit cell edge. So the unit cell edge is talking about the A. In the previous in previous videos that I told you. So if that is a BCC, the cell edge length, meaning the sides, this is the A. For the BCC, uh, A, that would be an A, of course, because all of them are A. So that is the distance between here and here. So of course, those are for a cube, that is the same for all throughout the uh, for all throughout the cube. They are all the same A's. And then A is 502 picometer, so A is given. That is 502 picometer. So we can already put the pico as negative 12 meter. Okay. And the density. So density is given is 3.50 grams per cc. So the density is given. So this is the physical density, 3.50 grams per cubic centimeter. So after that, using this information, calculate Avogadro's number. Occupied by 1 mole of atoms in a unit cell. Next, calculate the volume. A hint. First, calculate the volume in cubic centimeter. So we'll just follow this because it has a hint. First, calculate the volume in cubic centimeter. Okay. So we will calculate the volume. The volume is actually the unit cell is a cube. Okay. So a cube. calculate first the volume. What's that? Calculate first the volume in cubic centimeters. So we'll do that. Just follow this solution now. Calculate the volume, which is a cube for a cube, for a cube, yes, and that is in centimeters. So you have to 502 times 10 to the negative 12 meter. So we will equal this. This should be a cube because this is a, okay. This that should be a cube. For us to make it simpler, anyway, of course, I would be restricting you if you have another solution for this, but it will be similar. So I'll just get a negative 2 from here because it says that you have to calculate it in terms in centimeters. So I'll separate a 502 times 10 to the negative 10 and times 10 to a negative 2. Of course, 10 and 2, that would give us the 12. Because if you have the same base, you just add the exponents. But here, since we're doing it reverse, so we're just splitting the negative 12 into negative 10 and negative 2. That should give us the negative 12. Of course. And why? Why did you make it like that, sir? Because this is already the centi that we're looking for. So basically, if I'll put it outside, so mathematically, that should be 502 times 10 to the negative 10, and then now the cube, while this would now be as cubic centimeter. Okay, I'll just omit this first. Uh, that would be a centimeter. Of course, that is the centi times 10 to the negative 2, and then meter, and then cube. So again, since this is algebra, even though it's unit, it would still obey your algebra. And that should be a 502 times 10 to the negative 10. And now your unit now is cubic centimeter, which is what the problem said, that your unit should be a cubic centimeter. Okay, so that is now you already have computed. So let's just we may not put really the number. We just know that this is already the volume in terms of cubic centimeter. So, but anyway, we can compute that one, but maybe later. Now the next is calculate. Next is occupied 1 mole of the barium atom inside the unit cells. Next, first calculate the volume occupied by 1 mole of barium atoms in the unit cell. Okay. So the volume, this is the volume of um, the unit cell. So how many atoms are there for a BCC, body-centered cubic? There are two. So there are two atoms. So the volume of two atoms is this volume. Okay, because that's the volume of the unit cell. So we can say, because the hint is telling us to calculate the volume occupied by 1 mole of barium atoms, while this is two atoms. Okay, so meaning we could say the volume of uh, two atoms is 502 times 10 to the negative 10 raised to 3. Of course, you have still have the 3 cubic centimeter per two atoms. Okay, so that's really what it means by calculate the volume of how many atoms, because we are to find the Avogadro's number. So now the Avogadro's number really is the mass per the mass, or no, Avogadro's number is how many atoms are there. How many atoms are there in a um, atoms per mole? Okay, atoms per mole. So after this, next we look at the hint. Next, calculate the volume occupied by one barium atom in the unit cell. Oh, calculate the volume occupied by 1 mole of barium atoms in a unit cell. So 1 mole is calculate the volume occupied by one barium atom. Assume that 68% of the unit cell is occupied by barium atoms. Okay, 68% of the unit cell. 68% is occupied. So we only have to calculate 68 of this. I think it goes like this. Since we are given 68% only, so we still have to multiply this by 68%. 68% or 0.68. That is the volume occupied by those two atoms. Okay, because it tells us. So after that, um, I think we have to divide it in terms of 1 mole. So your barium atoms, we go to the periodic table. Our periodic table, let me pause first and let me get a periodic table. Okay, I pulled out a periodic table here. So we can look at barium, and barium has 137.327. So let's look out 137 327. 137 327. There is 137.327. The unit would be grams for every 1 mole. Okay. Uh, for every 1 mole, this is 137 grams. So after that, I think we only have to look at this. This is already the density. So let's plug out our density. Density is mass over volume, which is 3.50 grams per cubic centimeter. And then we equal it to mass, which is somewhat like this. Okay, and then we will see, because um, of course 137 point, I'm not looking at any formula. I'm just figuring out the dimensions, because this is the density. Of course, this is a formula, but the density is given, meaning the upper part should be mass, which is this one, 137.327 grams, and that is given in terms of mole. While the other side, we divide it with the volume, um, 5, 5.502 times 10 to the negative 10, the unit raised to cube, and then the unit is cubic centimeters per atoms. Now, Avogadro's number is well known to have a unit of atoms per mole. So, because that's what really Avogadro's number is, the number of atoms in mole. In fact, we know it already. I think it should be discussed already during your high school. That number should be 6.022 times 10 to the 23. Okay, but anyway, this is sort of problem. We just calculate Avogadro's number from the unit cell. But based on what I can remember, the Avogadro's number was not computed like this. So I think this later that it can be already be verified, that Avogadro's number really can be verified from your also from your cubic cell. I think the computation of your Avogadro's number is from the gases law, which is this is a solid. Okay. Anyway, for the sake of problem, so you can see you already have grams cancelled, and then cubic centimeter cancelled. So you will now have a unit of atoms, because this one is the divisor of the divisor. So that will go up here, of course, as if you're saying that um, you're dividing a fraction. So you invert that to make these atoms at the top. So what remains is, of course, those numbers. Of course, you can divide. So what will really happen is you can find the Avogadro's number if you can join these two one to information now. you can say that um, of course that should be the Avogadro's number should be the incorporation of this because that's a constant really. Okay? So an Avogadro's number usually we notate it as an Na. So we retain this one 137.327 and then this number here should go down, of course. It should go here, multiplied to this. So that should be a 502 cube. Of course, that cube should be distributed times 10. 3 times 10, that should be a negative 30. Okay? That should be a negative 30. And then you multiply 350 times 3.50. So the unit now is atoms per mole. Okay, and then you get your calculator. 137, I have my calculator. So, 137.327 divided by 502 cube. And then, um, times 10 exponent negative 30 uh, times 3.50. Okay, I don't know if if you can see that. So that should give me 3.1. Uh, 3.1. The answer is 3.1. You still have your 0.68. So where does that 0.68 will come? It should be at the bottom, 0.68. Okay? So you still have 0.68 multiplied by 0.68. So it should be included. 0.68 is it is given the hint. Okay? 68%. So I think it should be times 0.68. There is still your 502, then your 2. So times 2. Okay. So you have a times 2 at the top, and then you have a 0.68 times. What? Your 502 goes here. Volume. That should be 2 atoms. 0.68 volume. So that should give us times 2. 137.327. Then you have times 2 atoms. Then your 502. Is it 502 times 10 cube? That would be distributed, and then times 10 to the negative 10. So that should be 10 to the 30 times 3.50 times 0.68. That should give us I'll just post first so that we're not wasting time. So I think the 68 is not already included here. Why? Because it only gives us the that not all of the volume is occupied by atoms. In fact, we already have the two atoms which is occupying the unit cell. So I think this one should be erased. This one should be erased. It's only stated in the problem, uh, really to make us realize that not all of those cube will be occupied by atoms. So anyway, it's already included in the two atoms, as we've discussed the number of atoms per unit cells. For a BCC, again, that is the key. For a BCC, there are two atoms. We have already counted that. We have already established that. So I think I only need to, of course, uh, delete this 0.68, and then where are the two atoms? Atoms is at the top times two here. Okay, so times two. So I'll delete that 0.68. So that would be at the repeat. So may I get my calculator? So that should give us a 6.2. I don't know if you can see that, but the my value here is 6.20 times 10 to the 23. 6.20 times 10 to the 23. So actually, the Avogadro's number is already well known, and we will be using that actually for our solution, for the probably for the next problems. That should be a 6.22 times 10 to the 23. Unit would be particles per mole. While here for this problem, the units would be atoms per mole. Again, your Avogadro's number is a constant when we talk about a mole. Okay, so that's the concept of mole. That's a grouping of any particles. So if it will be talking about atoms, that would be a group of atoms. 6.22 times 10 to the 23 when we want to use that Avogadro's number. If those are molecules, then that would be molecules. If those are electrons, those should be electrons. Okay? As long as that particles is talking about atoms or a group of atoms like molecules or probably isotopes, ions, or even subatomic particles, protons, electrons. I have already seen computations from this, of course, in other chemistries. When you talk about electrons, when you talk about protons, with respect to the Avogadro's number. So this constant is a powerful one. So that's how we compute the Avogadro's number. So thank you for this problem.